In this video, we're going to learn how to find possible rational zeros with the rational zeros theorem. The rational zeros theorem tells us that for some polynomial function with integer coefficients, where p divided by q is a rational zero, then p is a factor of the constant term and q is a factor of the lead coefficient. So for example, suppose we're given x to the fourth plus 18x cubed plus 18x squared plus 18x plus 17 equals 0. Our constant term is 17, so that's p. Our lead coefficient, q, is 1. Possible factors of this ratio include plus or minus 1 and plus or minus 17. These are our possible rational roots. Now we can use the process of synthetic division to test our possible rational roots and find real roots. To set up our synthetic division, we'll take the coefficient from each term. So we have 1, 18, 18, 18, and 17. Note that if we were missing a term, perhaps we were missing 18x cubed, we would put a 0 in that spot. In other words, you need a placeholder for every exponential value. In this case, each exponential value is represented, so we just write their coefficients. And then, of course, we write our constant term, 17, at the end. Now let's test one of our rational roots, or our possible rational roots. Let's choose negative 17. We'll start by carrying down the 1. Negative 17 times 1 equals negative 17. 18 minus 17 equals 1. Again, negative 17 times 1 equals negative 17. 18 minus 17 equals 1. We repeat the process. Negative 17 times 1 gives us negative 17 again. 18 minus 17 gives 1. Negative 17 times 1 gives negative 17. And here 17 minus 17 gives us 0. So we know that we have found a root of our polynomial equation. Now we can rewrite our equation in factored form. So we have our root, negative 17. That's like saying x equals negative 17. I'll rewrite that as a factor by adding 17 to both sides. So I have x plus 17 times the remaining values of my polynomial. I have 1, which represents x cubed, plus 1x squared, plus 1x, plus 1, all equal to 0. Now we'll use synthetic division to test another root. Remember, our possible roots were plus or minus 1 and plus or minus 17. Well, we already found that negative 17 was a rational root, so let's try negative 1 with our remaining polynomial. 1, 1, 1, and then our constant 1. I'm just writing the coefficients for our variables and our constant term at the end. So we start by carrying down the 1. Negative 1 times 1 equals 1. 1 plus 1 or rather, I'm sorry, negative 1 times 1 equals negative 1. 1 minus 1 equals 0. Negative 1 times 0 equals 0. 1 plus 0 equals 1. Negative 1 times 1 equals negative 1, and 1 minus 1 equals 0. So here we have another actual root. So I know that I can take negative 1, x equals negative 1, add 1 to both sides, so I have x plus 1 equals 0, and I can add that in as one of my factors. So now I have x plus 17, the factor we found in the last step, times x plus 1, the factor that we found in this step, times our remaining polynomial, which is 1x squared. Then we have a 0 for our first power placeholder. And then we have a plus 1 for our constant term. Here we have a quadratic factor remaining. We can plug that into the quadratic formula. And you may already notice that this is going to give us 2 non-real roots. So let's see what it will look like. We have x plus 17 times x plus 1 times x squared plus 1. Let's take our x squared plus 1 and plug it into the quadratic formula. Negative b plus or minus the square root of b squared minus 4ac divided by 2 times a. So that gives us negative b, and we don't have a b term, so I'll put a 0 here, plus or minus the square root of 0 squared minus 4 times our coefficient, 1, times our constant term, c, which is also 1, all divided by 2 times 1. This gives us plus or minus the square root of negative 4 divided by 2, which gives us plus or minus 2i over 2, which gives us plus or minus I. So now we know that our solution set for our original equation, x to the 4th plus 18x cubed plus 18x squared plus 18x plus 17 equals 0, our solution set is negative 17, negative 1, I, and negative I. That completes our problem. I hope you found it helpful, and we'll see you next time.